Hello everyone, I am Assistant Professor Shendge Swapnil Sampatrao, Head of Department of Physics, KANMS Arts, Commerce and Science College, Satana, Nashik. So, friends, today we are going to discuss the Coulomb's law. In earlier stages, we have discussed the gravitational forces and gravitational constants in 12th science. In this year, we have to learn similar way, but that is the gravitational field and it is the electrical field. So before in going to in that field, we have to start with the electrostatics. So what is meant by electrostatics? It is a branch of physics that deals with phenomenon due to attraction or repulsions of electric charges but not dependent upon their motion. So electric statics is nothing but the study of electric charges which were attracting or repulsive from each other and which are not dependent upon their motion. That means the charges have a random motion. Okay, so these are the basic fundamentals laws of electrostatics. So here is comparison shown between Coulomb's law and Gauss's law. So Coulomb's law's formula is equal to law force, that means F equal to 1 upon 4 pi epsilon naught Q1 Q2 upon R square. So this Coulomb's law is very similar to the gravitational force, that means F is equal to G, capital G means gravitational constant, m1 m2 upon r square. Instead of m1 and m2, that means mass 1 and mass 2, here m1 m2 replaced by charge q1 and q2 respectively. Okay, so F is equal to 1 upon 4 pi epsilon naught q1 q2 upon r square. And in this Gauss laws, here integral form of Gauss law is given as closed integral E bar dot ds bar is equal to q enclosed upon epsilon naught. Q enclosed means charge in enclosed area. Okay, so for Coulomb's law, it is applicable to any kind of electrical point charge distribution. That means it is used for any type of charge distribution, that means random charge, non-uniform, uniform charge. For Gauss law, it is applicable to symmetric charge distribution. If there is any charge symmetry, then the Gauss law will be applicable. For Coulomb's law, second point, we can find electric field intensity, that means capital E, at any point due to point charge. For Gauss law, second point is it can only be applied to closed surfaces. Third point, for Coulomb's law, surface charge and volume charge distribution can be found. And for Gauss law, it is very easy to solve the surface charge and volume charge distribution. Okay, so this is nothing but the basic and fundamental between the Coulomb's law and Gauss law. So here is Coulomb's law. For the Coulomb's law, the statement is the force of attraction or repulsion between 2 point electrical charges at rest is first directly proportional to the product of magnitude of charges, that means q1 into q2. And second point, inversely proportional to the square of the distance between the charges, and it acts along the line joining the two charges. So friends, in this diagram there is 2 points shown, that means charge q1 and q2, and both are joining by the line or distance by r. So as per the statement of Coulomb's law, so F is equal to 1 upon 4 pi epsilon naught. So it is a constant term, that means 1 upon 4 pi epsilon naught. Epsilon naught is the permittivity of free space. So as mentioned for the first point, directly proportional to the product of magnitude of charges. So here charges is q1 and q2, so its product is q1 and q2, so it mentioned in this upper formula. And second point is inversely proportional to the square of the distance between the charges. So distance between the charges is denoted by r, and so we have mentioned the inversely proportional to the square of distance, that means upon r square. So f is equal to 1 upon 4 pi epsilon naught q1 q2 upon r square. So in vector notation it can be written as a bar is equal to 1 upon 4 pi epsilon naught q1 q2 upon r square into unit vector r. So Coulomb's law, f is equal to 1 upon 4 pi epsilon naught q1 q2 upon r square. Coulomb determined this constant was in vacuum is equal to 1 upon 4 pi epsilon naught, where epsilon naught is permittivity of free space and its value is 8.85 into 10 raised to minus 12 Coulomb square per Newton per meter square. So therefore by doing calculations finally we get Coulomb's constant, that means K. K means 1 upon 4 pi epsilon naught. So K is equal to 9 into 10 raised to 9 Newton meter square per Coulomb square. So F is equal to capital K into Q1 Q2 upon R square. Remember that K is nothing but the Coulomb's constant and its value is 9 into 10 raised to 9 Newton meter square per Coulomb square, and K is nothing but the 1 upon 4 pi epsilon naught, and epsilon naught is the permittivity of free space. Okay, so this is the application of Coulomb's law. The Coulomb's law is used to find the electric field intensity due to point charge. Electric field intensity is defined as force per unit positive test charge placed in that field, and it is a vector quantity and has direction of a force, and it can be written as E is equal to F upon Q naught. The unit is Newton per coulombs, and by using Coulomb's law, F is equal to 1 upon 4 pi epsilon naught Q into Q naught upon R square, because here we are mentioning two charges. One charge has a value Q and another charge value has a Q naught. Okay, so therefore by using electric field intensity formula, that is E is equal to F upon Q naught, we are replacing the value of F in E. So E is equal to 1 upon 4 pi epsilon naught into Q upon R square, because denominator Q naught and numerator Q naught cancels each others. Okay. Another application of Coulomb's law is to find the electrical potential due to point charge. Electric potential at a point in an electric field is defined as the work done per unit positive test charge to bring it from infinity to that point without accelerating the charge. Therefore V, that means electric potential, V is equal to work done, that means W upon Q naught, work done per unit positive test charge. So V is nothing but the electric potential, W means work done, and Q naught is nothing but the positive test charge, where W is equal to integral F dot dr bar, that is the work done. So by using Coulomb's law, we get W is equal to 1 upon 4 pi epsilon naught Q into Q naught upon R. So replacing the value of W in the V, so V is equal to 1 upon 4 pi epsilon naught into Q upon R. Again here Q naught, numerators and denominators value cancels each other, and we get the final value V is equal to 1 upon 4 pi epsilon naught Q upon R, joule per coulomb or volt. There are some limitations of Coulomb's law, and these limitations are as follows. That means the Coulomb's law can be only applied in those cases where the inverse square law is obeyed. Otherwise, it cannot be applied for that such a laws. It is difficult to implement Coulomb's law where charges are in arbitrary shape, because in such cases we cannot determine the distance between the charges. That means in when the charges in arbitrary shape, we cannot check, or we cannot measure the distance between two charges exactly, and that's why we cannot use this law over there. It cannot be applied for distance less than 1 Fermi. For very small distance between two point charges, it cannot be applicable. Another limitation is Coulomb's law cannot be applicable for moving charges, and this is not for the moving charges. And lastly, thank you one and all. Thank you.